Hey everyone, welcome back. This is an appendix lecture that will complement the buffer overflow lecture I just did. And it's going to be a very brief intro into reverse engineering techniques with a focus on static binary analysis. And this is going to be probably the bare minimum reverse engineering techniques that you may need to complete this homework. And in addition to binary static analysis techniques, we're going to be going over the evolution of code of a software program from source code to binary file. And at the machine level, all data is an array of bytes, and the interpretation depends on the instruction used. And at the highest level, you have interpreted languages or model level, high level languages that have a strong notion of type and valid operations, but you don't typically access memory, so this is why they're not vulnerable to buffer overflows. So if you're writing in Python code, you're not allocating any memory or doing any direct memory access, and this can occur some overhead. So that's why C and related languages that are lower level have these high level control structures that allow you to have direct access to memory. And this is why they're vulnerable to these buffer overflows. But at the same time, they do have a large legacy use because in embedded systems, sometimes you do need to have uh, precise memory access and real-time constraints for your system, and you have to have deterministic behavior. And there are two types of or categories of reverse engineering techniques: static and dynamic analysis. And for static binary analysis, the purpose is to analyze the static nature or structure of these files. And you can intuit a lot of information just based off the static information, and we'll show some examples of what I mean by that in a bit. And also, reverse engineering techniques are used a lot in malware analysis. So if you're analyzing malware, for example, you don't have to actually run the code or anything. You can just look at the snapshot of the binary before it's run. But there are a lot of drawbacks from this. You do miss a lot of the dynamic behavior in static analysis, and it's very time consuming. And also, if you are analyzing malware, then it could be subverted by anti-reverse engineering techniques, but we're not going to go into that in this lecture. And in addition to not only missing dynamic behavior, there are some very complex programs, and this is why it's time consuming. So for example, if you have a starting point here, this is a static snapshot of some firmware that I've extracted in the past, and there's so many different paths you could take, and depending on the state of your system. So at using dynamic techniques, you would be able to trim some of this, but if you just look at this statically, it'd be difficult to navigate, and you wouldn't even understand what the true behavior of this system was. You would just know that there are some sequence of instructions and some control flow paths that it might take. And for dynamic binary analysis, the goal is to analyze the features of the binary at runtime. This could be, your network communications, any file operations that it's doing, or how it's interacting with the operating system that you'd only see when you actually run the code. And there are several pros to this. So for example, data functions will always need to be valid at runtime. So if they do use some of these anti-reverse engineering techniques, then for example, like if you encrypt or you compress part of your code, it needs to be unencrypted or uncompressed at runtime to actually run on the system. And it is faster because these dynamic signatures would significantly reduce not well it would significantly reduce kind of the control flow analysis of your static reverse engineering techniques, but it would also it could provide some easier intuitions about the system. So if you're using some network analysis, you could see what websites they're connecting to and so on. And there are some immediate drawbacks from this. So it actually requires running the code. So this is, well, for one, it could be challenging if you don't know if you need to emulate the hardware, and especially for example, if you extract the hardware of some cyber physical system or a controller on a cyber physical system, you need a way of emulating all the peripherals and the sensors and actuators of your system, so that you actually get the true state of the system in operation. And there's also some drawbacks too. If you're, for example, if you're analyzing malware, you would actually have to run the malware. So this could also be a problem. And it's useless without static analysis, as it needs context. So in the previous slides, we showed this very large control flow structure. If you use dynamic binary analysis, then you could have an understanding of where the program is and what instructions it's running and so on. So we're going to ignore dynamic binary analysis for this lecture because it's not necessary for the assignment that you guys have. There are some basic techniques that you can do to save you some time if you want to just extract some high-level features of the binary. So, for example, for static analysis, you can actually look at the binary without actually going into the instructions. So, for example, for malware, there are tools like VirusTotal that can look at the signatures of the binary just by taking a hash and seeing if it matches any other virus that may have been loaded onto their database. And then there's the string functions that shows you all the strings, and we'll discuss that in a bit. And these are quick and easy, but they fail for advanced binary analysis and can miss important behavior. And then there are some basic dynamic techniques where you can use some tools to just test in a safe test environment, but it's not effective on all binary files. And for the more advanced techniques, you'll have, for example, in static analysis, you could do reverse engineering with a disassembler, which is what we're going to go over today. And it's complex and does require understanding of assembly code, but we'll show some basic techniques today that will help you get through this assignment. And you could always ask me questions if you need if you're stuck on anything. And then for advanced dynamic analysis, one example would be running the code in a debugger to examine the internal state of a running executable. So several of you have used debuggers in the past for code. In this case, you could use it to actually for reverse engineering to analyze the internal state. And as I mentioned before, we're going to focus only on the static binary analysis techniques, as there are entire courses on binary reverse engineering techniques. And the course I took in my PhD was practical malware analysis. And even though it was in the context of malware reverse engineering, these techniques apply to any other binary that you're trying to figure out what it is that it's doing. Okay, let's get into it. So there are various levels of abstraction that we need to know to understand how a program is compiled and run. So at the lowest level, you have your hardware, which are all your digital circuits and logic gates that aren't easily manipulated by software. Then above that, you have your microcode, which is sometimes referred to as firmware, that operates on specific hardware. Then just above that, you have the machine code, which are your process level instructions. And this is the end result of actually when your high level language is compiled. Then you have low level languages. This is your assembly languages where probably the first point where you actually get human readable versions of processor instructions. And then we have our higher level languages like C and C++ that can be directly converted to machine code. And at the highest level, we have interpreted languages that we mentioned before that are not directly translated to machine code. Usually have some intermediate representation, such as bytecode, that is run on some interpreter, and that interpreter takes care of translating it to the machine code. So I've mentioned this word disassembly in the past, and the definition is in the word itself, because when we write code, the program is translated into some machine level representation, and then what we do with disassembly is we disassemble it, or we take the machine code and lift it to some higher level abstraction, and usually it's to convert it from machine code to assembly. And the most popular disassembler is IDAPRO, which we'll get to in a bit. But before we get into IDAPRO, there are some simpler command line static techniques that you want to be familiar with. So these three: strings, object dump, and readelf. So let's say we have this sample code here where in the main function you're just printing hello world, and then it calls func1, which just prints in func1. So if we compile this with GCC, and let's say we use strings on the binary, so these virtual machines can be tricky when it comes to input. Test.o, you'll see all the strings listed in your binary file. So actually, if you pipe this out, if you pipe the output using this pipe command, and if you pipe it into something like less, you could actually navigate this more easily. So you can see some of the strings from our code. You can see in func1 and hello world here, and the other ones are, for example, object dump, and there's a particular you could look at the man page for this. I linked it in. You could look at the man page for any of these programs. So object dump will provide you with information from the object files, and we'll get into object files in the next slide. But there is one particular command line option that you can use, -D, and that will disassemble your code. And this is going to be what I mean by disassembly. Whoops. Object dump. If I can type correctly and spell correctly, then we could see what it does. So here, well, let's pipe it into less. Or if you don't want to pipe it into less, you don't like command line, you could also pipe it into just any output.txt file, for example. And from here, we can then open it with any command line, any editor that we'd like. So I use Guinea. So here, you can see these are all the sections of your code, and this is actually I'm not going to get into what every component of or every section of this binary file is, but we can, for example, look up our main functions and see all the code there. So this is libc start. So this is our main function here, and you could see it should have references to the strings, and we'll get into cross-referencing with IDAPRO in a bit. But this is just a very simple way of looking at the assembly instructions of what's running for each function. You can see func1 up here, and IDAPRO is has a GUI that's nicer and makes this much more pleasant to work with, and we'll see it in a bit. And then the last command that I want to get into is this readelf, and this will print metadata about your binary. So these are all the header sections of your code, and you could oh, sorry, you have to use readelf -a, and then this is to print all the headers of your file. And headers are just metadata sections of your binary, but it could be useful for debugging. So let's say we pipe it into less, and you could see these are just some information about your file. This one may not be as useful for you, but for future reference, when you start to learn more advanced reverse engineering techniques, you'll see that it's good for identifying different sections of your code. And just a quick note, at compile time, a compiler uses a symbol table to keep track of several components of a code in what's called the object file, and this will keep track of things such as your variable names and constants, and procedures and function names, and all these things that you need for debugging. So to conceal this information, developers may actually strip the symbols from a binary before distribution. So for example, you wouldn't be able to load it in GDB and then reference specific variable names. So in these contexts, you would use the strip command to strip the files in Linux. So now we can get into IDAPRO, which is going to be the meat of this presentation. And IDAPRO was developed by Hexrays, and it's free. So actually, this screenshot is a little bit old. It's from version 5. I think the freeware is now up to version 7. And you can go to hexrays.com, and you could actually see this is actually running an iteration of IDAPRO. So if we go to hexrays.com, or you could just Google, IDAPRO download, and you could go to the download center. I will say that it didn't work. The freeware didn't work on Mac, so it definitely works on Linux. So if you're already running the virtual machine with Linux, which I'm doing here, you can just run IDAPRO. And this is actually shows IDAPRO opening up our previous test file, and you can see this is just printing hello world, and I think you could probably see func1 here if you like. So there are going to be a bunch of basic tools and techniques that you use in IDAPRO, but I guess first I'll actually show you how to open a file in IDAPRO. So when you install IDAPRO, you'll probably get a desktop icon that you can run. You press OK, and you say disassemble a new file, and let's say I go to test.o, which I think is right here. You could select it, and you want to I'm just starting from scratch here. You could usually auto detects what type of file it is, so you could just use the default parameters, and from here it will load everything, and you'll start out in graph mode, and you can see these are all your function names here, and you go to each one. There's func1, there's main, and it usually starts out in main. And you could switch between graph mode and text mode using the space bar, and that will allow you to the graph mode will it's nicer when you're looking at control structures. So if you have if statements, for example, those will be broken down into two different branches here, but then in the text mode you can get a more detailed view of the address space, and as well as the assembly code. And so both are useful, and you're going to find that you could switch back and forth. So the default will be the graph mode display, and there's a bunch of line options that you could play around with. So line prefixes is nice, and then the number of opcode bytes that you're using. I think for this assignment you're probably okay just using the default files, but these are things you could look into in the future, or if you have more questions we could talk about it. And it will provide, so for example, before, if you enable line prefixes, it will allow you to see some of the address space in the graph mode view. And you will find the arrows for different control structures. So, for example, a red arrow will be a conditional jump not taken. Green will be conditional jump taken, and a blue will be an unconditional jump. And if there's a while loop, you'll see that, or any loop, you'll see an arrow that points back to itself. It's pretty intuitive. So this is an example of a branch where you have a red arrow if the branch isn't taken, and a green one if it is, and then both of these go back to the same point after. So this is an unconditional jump between sections of code. And there's highlighting. So when you highlight a particular, for example, the EBP, it will highlight every instance of that text, which is nice when you're, for example, trying to see where this variable 4 might be throughout the text. And in text mode, yes, you could see there are arrows as well that have similar meaning, where solid is unconditional, dash is conditional, and up is a loop. And there are comments that are automatically generated. You could see these, I believe you could see these both in graphical mode and text mode as well. And here, so the commenting generated by Adapro is actually very nice, because, for example, here in the assembly code, it will tell you, okay, this refers to this particular string that you'll, if you actually look at our main function from before, it's showing that the string variable is actually stored somewhere else, but we know what the string is when it calls puts, which is equivalent of printf. And so yes, there's a whole bunch of comments you can play with. So auto comments will add comments to each instruction, and this is nice, especially if you forget your assembly. It will tell you what each assembly line is. So this auto commenting is nice. And there are several useful windows for analysis. So as I mentioned before, the functions will show each function, the length, and the flags. And if it says L, it'll be a library function, and it's sortable. So usually the larger functions are the most important. And there's names, so these are all the names of your functions, your name code, name data, and strings. And what's nice is that you could actually modify the names. So if you see that there's some arbitrary variable like var4 that we saw here, if I go back to our variable here, so you could rename var4 to have some more semantic meaning, like, this is variable X, or it represents some sensor value or something like that. And that'll be nice just to keep track, and you don't have to remember what var4 is throughout the rest of your analysis. And then the strings window does the same thing as the strings function that I mentioned before. It's just going to show you in the nice GUI, these are all the strings of your code. But what's good is that you can actually click on a string, and it will go to, you can look at the cross references. So when I say cross references, you'll see where it's used in the code. And then these are just the imports and exports. You don't have to worry about this too much. This is actually, here they're showing actually Windows programs, but it'll show you what's being imported and exported from the program. These are just libraries that it's using. And then the structures will show you if it could see any active data structures, and you could hover over each structure and see what is the yellow pop-up window associated with that. And this is what I mentioned before with cross references, where you could double click a function, and then you could see where it is in code. And you could do this for variables as well, to see where variables are being used and referenced. And when you see a function call, you could look at what parameters are moved onto the stack, and you can see a call to a particular start function. So that'll be useful when looking at function calls. And now we'll talk about just simple navigation of IDA Pro. So importing imports or strings, you could double click any entry and display it in the disassembly window. And links are useful, so if you see any link on there, you could just double click any address in the disassembly window and it'll actually go to that location. And this is pretty intuitive. You'll be when you play around with it, you'll see how easy it is. And history's useful to essentially, it's like a forward and back button. So if you go to a bunch of functions and then you find, oh, I want to go back to that function I went to before, you could just see what your execution trace was. And there's a navigation band that you'll see at the top that will essentially show how your code is broken down, and light blue will be library code, red will be compiler generated code, and dark blue would be user written code. And this is usually what you want to analyze. And usually there'll be some parts of the code that aren't disassembled for binaries that are stripped, or you may have put a wrong offset address. Usually this full blue means that everything has been disassembled for the most part. And if you press G, you could jump to a particular location. So if you remember that, a particular function is at a certain location or strings, you could jump to that particular address, and you could search. So this is really handy when you want to search for a particular string. So if you know that if you find a string in the strings function, like on Linux, and you want to search where it is, or the next instance of it is, you could use, for example, a search for string or sequence of bytes or whatever it is that you're searching for. And just another note about using cross-references. So code cross-references are nice, and usually there's an xref comment that's generated. You can see code xref. It shows where this function is called. But by default, it usually only shows a couple of cross-references, so you may have to do a little bit more digging. To see all the cross-references, you could click a function name and just press X, and you'll see all the places in your code where this particular function is called. And then there's data cross-references that I mentioned before, where you could look at your strings and you could double-click it. Any interesting string. So for example, if here they're talking about like a file name, and you could hover over it and see where that string is used. And again, you could use X to see all the cross-references. So we'll talk a little bit now about analyzing functions. So when you're looking at a function and you want to recognize the arguments being passed, IDA Pro will typically identify the function, name it, and also name any local variables. So these are, for example, arg0, arg4. These might be 3 integer arguments, but you have to be careful because it's not always correct. So sometimes it's good to double check and not put all your faith in IDA Pro. And there are graphing options that are helpful as well. So for example, printing the flowchart or the function calls, or all the X references to and from a particular function. And there are what's called legacy graphs that can't be manipulated with IDA. And the first two, these are kind of obsolete because the flowchart creates a flowchart of the current function, and function calls will provide a graph function for the entire program, but this is already kind of implicitly provided by the current state-of-the-art for IDA Pro. And the xref to and from can show you, as I mentioned, all the charts. And finally, for this last section, I just wanted to show some techniques to enhance your disassembly. So as a fair warning, there's no undo. So if you make any changes and you mess them up, you may be sorry. So be sure to save your work and just be very careful when you're making changes to some of the auto disassembly. So one technique you use is rename locations. So for example, a lot of times in stripped files, you may have subroutines or functions that are important, and you may want to rename a particular address to say, hey, this is, for example, reverse backdoor thread. And if you change it in one place, IDA will change it everywhere else. And this is just an example of some code that has some renamed arguments. You see on the left how you're dealing with arg4 var 598. Whereas if you know this is a port string and a port, it's very easy to kind of, as a human, to read this and see what the code is doing. And you can also add your own comments. So, if you just want to, annotate some code, you could press colon to add single comment or press semicolon to echo this comment to all cross references. So these are just some useful techniques. And you could also format a particular operand. So for example, here, if we're moving a particular value into EAX, it may be easier to see that, for example, I could put it in different representations, whether it's a decimal value or a hex value. It could have some semantic meaning that's that makes the program more easy to read for yourself. So for example, if it's in binary format and you want to switch it to an integer because you know that it's some integer like 3 or 4 that is more easy to read, then that might help just with your understanding of the code. Same thing for using named constants. You can use these named constants to make the arguments more clear. And finally, you can extend IDAPRO with plugins. So there's a whole course you could do on writing plugins for IDAPRO with Python, and you could look these up online. But again, this was a very, very brief intro to IDAPRO, and I think that really just opening up the files in IDAPRO and just navigating them with the graph mode and text mode should suffice for this assignment. And be sure to ask any questions and put your questions on the forum if you have any, and I'll do my best to answer them as fast as I can.